Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine looking at a star system that is practically an infant, like just a few 100,000 years old.
Right. In cosmic terms, that star has barely even ignited.
Exactly. The surrounding disk of dust and gas is still chaotic, it's hot, and it's incredibly thick. And yet, orbiting incredibly close to this baby star, you see a massive, fully formed gas giant.
Yeah, a planet 4 times the mass of Jupiter, just sitting right there in the data.
According to every established law of physics, every textbook on planetary formation we have, and every mathematical model we've spent the last century perfecting, that planet should not exist for another 10 million years.
It absolutely shouldn't. It's impossible.
And yet it's there. Welcome to March 2026.
It really is the ultimate paradox in modern astronomy right now. We are staring at a cosmic impossibility that just refuses to go away.
It's wild.
Yeah.
Because for decades, the astrophysical community has operated under this relatively stable paradigm regarding how solar systems actually come into being, right?
Yeah, the timeline was considered totally non-negotiable. Building a planet, particularly a massive gas giant, is this incredibly slow, painstaking process.
Right. You're accumulating microscopic dust grains into pebbles, and then pebbles into boulders, and eventually forming a core massive enough to sweep up a thick atmosphere.
Exactly. So finding a fully formed gas giant around a star this young is, well, it's like walking into a delivery room and finding a newborn baby with a master's degree in astrophysics.
That is a perfect analogy. The timeline is just completely shattered.
Totally shattered.
Okay, let's unpack this. We're going out to the absolute bleeding edge of current human knowledge today. We need to look exactly at what it means when an observation is officially declared to, quote, defy planetary formation.
Which is a heavy phrase in science.
It really is. So we're going to dive deep into the specific mechanics of this newly announced discovery from the CHEOPS Space Telescope.
And we'll explore the shock waves this single, anomalous piece of data is sending through laboratories and observatories around the globe right now.
Yeah, and most importantly, we're going to look at why breaking the fundamental rules of the cosmos is actually the most thrilling, vital thing that can possibly happen in the scientific process.
Because the scientific method really thrives on friction. When observation aligns perfectly with theory, it's comforting, sure.
But it doesn't push the boundaries, right?
Exactly. It doesn't push our understanding at all. It's only when our map of reality completely fails to match the territory we're observing that true discovery happens.
An incomplete or broken map is basically an invitation to redraw the universe.
And CHEOPS has just handed us a piece of the territory that makes absolutely no sense on our current map.
So let's start by grounding this in the specific instrument that threw this curveball. Because to understand the break in the rules, we really have to understand the observer.
Right, the tool making the observation.
Yeah. The announcement that just dropped centers on data from the Characterizing Exoplanet satellite, or CHEOPS.
CHEOPS, yeah.
And for anyone following exoplanet science, CHEOPS isn't out there blindly sweeping the sky hoping to get lucky like Kepler or TESS did.
No, not at all. It is a highly specialized precision follow-up mission.
Right. It deliberately targets stars we already know have planets, and it measures them with a level of accuracy that is, frankly, hard to comprehend.
That distinction is crucial. CHEOPS is not a discovery engine. It is a refinement engine.
Okay, tell us about the actual hardware.
Well, its primary instrument is a Ritchey-Chrétien telescope feeding into a single incredibly sensitive charge-coupled device, or CCD.
A CCD, right.
Yeah, and it operates on the principle of transit photometry.
So looking for shadows, essentially.
Basically, when a planet crosses the face of its host star from our line of sight, it blocks a minuscule fraction of that star's light. We are talking about measuring a dip in stellar brightness on the order of parts per million.
Parts per million. I was actually looking at the supplementary data released with this announcement, and the error margins on the photometric data are insanely tight.
Oh, they're unbelievable.
We are talking about an instrument precision of something like 10 parts per million for a sun-like star.
Right.
To put that into perspective for you listening, that is essentially trying to measure the dimming of a car headlight in Los Angeles because a single mosquito flew in front of it while you're standing on a rooftop in New York City.
That analogy perfectly captures the engineering triumph of this mission. CHEOPS achieves this precision because it operates in low Earth orbit far above the atmospheric distortion that plagues our ground-based telescopes.
No twinkling stars to mess up the data.
Exactly. Furthermore, it is deliberately defocused.
Wait, defocus? Why would you want a blurry telescope?
It sounds counterintuitive, right? But instead of focusing the starlight into a sharp point, it spreads the light over many pixels on the detector.
Oh, I see.
Yeah, this mitigates the effects of tiny pointing jitters from the spacecraft and also any variations in individual pixel sensitivity. It allows for an ultra-stable, ultra-precise light curve.
And the shape of that curve, like the depth of the transit, the slope of the ingress and egress as the planet enters and exits the stellar disk, that tells us the exact physical diameter of the planet relative to the star.
Yes, exactly. But diameter alone isn't enough, which is where the broader astronomical community comes in.
Right, because you need more than just size.
You take that incredibly precise volume measurement from CHEOPS, and you combine it with the radial velocity data.
That's the gravitational wobble of the host star, right?
Exactly. The wobble measured by ground-based spectrographs like HARPS or espresso. Radial velocity gives you the planet's mass. Mass plus volume equals density.
And density is the holy grail.
It really is. It tells you if you are looking at a fluffy cloud of hydrogen, a dense cannonball of iron, or, a deep ocean world.
Right. But the tension we are looking at in March 2026 isn't just about what the planet is made of. It's about the fact that it exists at all in its current environment.
Yeah, that's the real issue here.
Because there is an enormous fundamental tension right now between observational astronomy, the hard, unyielding data streaming down from CHEOPS, and theoretical physics.
Which provides the complex mathematical frameworks for how matter is supposed to behave in a protoplanetary disk.
Exactly. Theories of planetary formation are beautiful, highly balanced equations based on thermodynamics, fluid dynamics, and gravity.
And CHEOPS has just delivered a high-resolution, undeniable profile of a celestial body that the math absolutely insists is impossible.
I have to push back here, though. Because my first instinct, and probably yours listening to this, is profound skepticism.
Of course.
Before we throw out a century of theoretical physics, shouldn't we interrogate the machine? Is it possible CHEOPS just glitched?
It's the first question everyone asks.
I mean, we are talking about measuring 10 parts per million. Could a stray cosmic ray have hit the CCD sensor at the exact wrong time?
Or, could the star itself be exhibiting extreme stellar activity?
Right. Star spots or massive solar flares that the software pipeline misinterpreted as a planetary transit. We have seen massive false alarms in physics before.
Oh, absolutely.
You think back to the BICP2 announcement about primordial gravitational waves that turned out to be galactic dust, or the faster-than-light neutrinos in Italy that ended up being a loose fiber optic cable.
I remember that cable.
Yeah. So why are we so sure the telescope isn't just lying to us?
What's fascinating here is that the scientific community's initial response is always exactly that, ruthless skepticism.
They don't just accept it.
No, astronomers do not want to rewrite the foundational textbooks. It is exhausting, career-upending work. In modern astrophysics, a discovery of this magnitude undergoes a gauntlet of validation that is almost adversarial in nature.
Adversarial. I like that.
Yeah. When the anomalous light curve was first downloaded, the CHEOPS science team didn't pop champagne. They immediately assumed they had made an error.
So they essentially tried to kill their own discovery.
They spent months trying to destroy their own data. They ran rigorous detrending algorithms to isolate and remove any instrumental noise.
Okay, so filtering out the static.
Right. They factored in the thermal stability of the telescope tube. They meticulously mapped the background sky to ensure a fainter, eclipsing binary star in the distance wasn't contaminating the target star's pixels.
Wow, so checking for photobombers, basically.
Exactly. And they modeled the host star's rotation and magnetic activity to separate star spot-induced light variations from a true planetary transit.
That is incredibly thorough.
And then they handed the raw, unprocessed data to independent rival research teams and challenged them to process it using entirely different software pipelines.
And every single time, the planet was still there. The anomaly survived the gauntlet.
The signal remained robust across every independent analysis. The transit depth is real. The orbital period is real.
Okay, wow.
The fact that the European Space Agency and the global astrophysics community are stepping up to the podium and explicitly framing this as a discovery that, quote, defies formation, rather than quietly cataloging it as an unresolved data anomaly, That signifies the immense weight and the highly verified nature of the CHEOPS observation.
So they didn't just check the metaphorical fiber optic cable. They rebuilt the entire interpretive framework from the ground up, and the impossible planet refuses to vanish.
The data is solid. It is our theories that have suddenly become incredibly fragile.
That sets the stage perfectly. The observation is real, the anomaly is confirmed. So that forces us to move into the actual mechanics of the mystery.
All right, the physics of it all.
We need to deconstruct this idea of defiance, because to understand how a cosmic law is broken, you have to really understand the intricate machinery of the law itself.
You have to know the rules before you can break them.
Exactly. What does it actually mean to defy planetary formation? We aren't talking about a minor discrepancy like a planet having 5% more carbon than the models predicted.
No, nothing that trivial.
We're talking about a fundamental contradiction of the established sequence of how matter coalesces from the void into a macroscopic world.
To appreciate the defiance, we really have to look deeply at the rulebook. For decades, the undisputed champion of planetary formation theory has been the core accretion model.
Core accretion, okay.
It's the framework that successfully explained our own solar system. Picture a newborn star surrounded by a protoplanetary disk, a massive, spinning, flattened cloud of leftover hydrogen, helium, and microscopic dust grains.
Okay, I'm picturing a giant cosmic pancake around a light bulb.
That works. Now, the physics of how you get from a microscopic dust grain to a gas giant like Jupiter is shockingly complex and fraught with bottlenecks.
Well, it's not just gravity pulling things together from day one, right?
Yeah.
Because dust grains are way too small for their gravity to matter.
Exactly. In the earliest stages, gravity is completely irrelevant. The dust grains, which are essentially microscopic silicates and carbon compounds, they collide purely by chance as they are carried along by the gas currents in the disk.
Just bumping into each other in the dark.
Right. And when they collide, they stick together through electrostatic forces, Van der Waals forces. It is the exact same physics that causes dust bunnies to form under your bed.
Okay, so cosmic dust bunnies. I can visualize that.
These fractal, fluffy dust aggregates slowly grow over tens of thousands of years. They go from the size of a grain of sand to a pebble to something the size of a golf ball.
But there's a massive physical hurdle they have to overcome here. I was reading about the meter-size barrier, which seems like the point where the entire process should theoretically just fail.
Oh, the meter-size barrier is one of the most notoriously difficult problems in the core accretion model. As these clumps of dust grow to about a meter in size, like the size of a boulder, they decouple from the gas flow.
Decouple, meaning they stop moving with the wind.
Basically. The gas in the protoplanetary disk is supported by internal pressure, so it orbits the star slightly slower than a solid object would.
Okay.
Therefore, a meter-sized boulder is orbiting faster than the gas around it. It experiences a constant headwind.
Like riding a bike really fast on a still day. You feel the wind pushing back.
Exactly. And this headwind saps the boulder's orbital momentum, causing it to rapidly spiral inward and burn up in the host star. Mathematical models show that a meter-sized rock should spiral into the star in just a few hundred years.
Which is incredibly fast in astronomical terms, like the blink of an eye. So how does anything ever survive to become a planet? How do we get past that barrier?
Nature requires a rapid, almost violent workaround. The current leading theory is that turbulence and eddies in the gas disk create localized pressure bumps, essentially cosmic traffic jams.
Cosmic traffic jams, okay.
The boulders get trapped in these pressure bumps, accumulating in massive numbers until their collective gravitational pull finally kicks in.
So they gang up on the headwind.
Right. This triggers a localized gravitational collapse, instantly bypassing the headwind problem and forming planetesimals. These are solid bodies the size of cities or small continents, ranging from 10 to 100 kilometers across.
Okay, so now we have the building blocks. We have city-sized asteroids crashing into each other, but building a rocky planet like Earth is vastly different from building a massive gas giant like Jupiter.
Fundamentally different, yes.
And location plays a critical role here.
Right.
You can't just build a Jupiter anywhere.
Location is everything, and it's governed by the concept of the frost line, or snow line. As you move away from the intense heat of the young star, the temperature of the protoplanetary disk drops.
Naturally.
At a certain distance in our solar system, it's roughly around the asteroid belt, it gets cold enough for volatile compounds like water, ammonia, and methane to freeze into solid ice grains.
And ice is the game changer for building gas giants.
It is the absolute catalyst. Inside the frost line where it's too hot, Planets can only be built from rocks and metals, silicates and iron.
Which are pretty rare, relatively speaking.
Very rare. They comprise only about 1% of the total mass of the disk. That's why Earth, Venus, and Mars are relatively small. But outside the frost line, you suddenly have access to an enormous abundance of solid ice.
Because all that water vapor suddenly becomes solid building material.
Exactly. This provides 4 to 5 times more solid material. Planetesimals outside the frost line can grow incredibly fast and incredibly massive.
They enter a phase of runaway growth.
Yes. Once an icy, rocky core reaches a critical threshold, about 10 times the mass of the Earth, its gravitational pull becomes so immense that it can begin to rapidly suck in the surrounding hydrogen and helium gas directly from the nebula.
Just vacuuming up everything around it.
This is the runaway gas accretion phase. Over the course of a few million years, this 10 Earth mass core sweeps up hundreds of Earth masses of gas, ballooning into a Jupiter or a Saturn.
Wow.
But here is the absolute bedrock requirement of the core accretion model. This entire process takes time. It takes at least 2 to 5 million years for the core to grow large enough to initiate runaway gas accretion.
And the clock is kicking the entire time, right? Because the protoplanetary disk doesn't last forever.
The disk is highly transient. The young host star is blasting out intense ultraviolet radiation and powerful stellar winds.
So it's basically blowing away its own planetary building material.
Exactly. This process, known as photoevaporation, is actively blowing the hydrogen and helium gas out of the system. Typically, a protoplanetary disk completely dissipates within 3 to 10 million years.
So it's a race against time.
A literal race. If a planetary core doesn't reach the critical 10 Earth mass threshold before the gas is blown away, it fails to become a gas giant. It ends up as an ice giant like Uranus or Neptune or just a barren rock. The timing must be perfect.
Here's where it gets really interesting. We've established the unbreakable rules. You need millions of years to build the core. You need the cold temperatures beyond the frost line to get the ice to build that core quickly.
Right.
And you have a strict deadline before the star blows all the gas away. Now let's bring in the specific CHEOPS discovery from March 2026.
This is where it all falls apart.
We're looking at a host star. It is only 300,000 to 500,000 years old. It is an infant. It is still practically in its stellar womb. And yet, orbiting at an incredibly close distance, well, inside the frost line, in a region where the temperature would vaporize any ice, is a fully formed, massive gas giant.
It is a devastating contradiction. A 500,000-year-old star should only have microscopic dust grains or perhaps a few early planetesimals swirling around it.
Dust bunnies, not Jupiters.
Right. The gas giant we are observing has bypassed millions of years of necessary evolutionary steps. Furthermore, its location is entirely wrong.
Because it's too close to the heat.
Being that close to the star, inside the frost line, there simply wasn't enough solid rock and metal to build the critical 10 Earth mass core required to capture the gas. The math does not work. You cannot build a planet of that mass in that location in that amount of time using the core accretion model.
So if the established recipe is wrong, we're forced to speculate on alternative mechanisms. If it didn't form slowly from the bottom up, how did it get there?
We have to look at other options.
I know there is an alternative theory that often gets discussed for massive planets far away from their stars called disk instability. Could that apply here? Could a planet form top-down like a star does?
Disk instability is the primary alternative to core accretion, and it is certainly dominating the frantic discussions right now.
How does that work?
Well, in the disk instability model, you don't need to slowly build a rocky core. Instead, if the protoplanetary disk is massive enough and cold enough, a localized region of the gas can become gravitationally unstable.
Like a sinkhole forming in the gas.
Kind of, yeah. It rapidly fragments and collapses in on itself, forming a massive gas giant in a matter of thousands of years rather than millions. It bypasses the pebble accretion, the meter-sized barrier, and the core building entirely.
It's essentially a shortcut.
Yeah.
The gas just instantly crushes itself into a planet. But wait, you said it requires the disk to be cold enough?
Yes.
This CHEOPS planet is sitting incredibly close to the young star. The ambient temperature from stellar irradiation would be massive. Doesn't heat prevent gas from collapsing?
That is the exact friction point of this hypothesis. Thermal pressure pushes outward. For a gas cloud to collapse under its own gravity, it must be able to radiate away its heat efficiently.
And if it's next to a baby sun?
Right. Close to a star, the stellar irradiation keeps the gas hot and pressurized, stabilizing it against collapse. Traditional disk instability models require the planet to form very far out tens of astronomical units away in the deep freeze of the outer system.
So if it formed far away via disk instability to avoid the heat, how did it end up practically touching the star?
That requires invoking violent planetary migration. We have known since the discovery of the first hot Jupiters in the 1990s that planets do not necessarily stay where they are born.
They move around.
They interact gravitationally with the surrounding gas disk. In a process called Type 2 migration, a massive planet opens a gap in the disk and is essentially carried inward as the disk material accretes onto the star.
Like a surfer riding a wave towards the beach. But the timeline is still the killer, right? Even if it formed far out via instability and surfed the disk inward, migrating takes time.
It takes hundreds of thousands to millions of years to have a massive planet form via instability in the outer disk and then migrate all the way to the inner edge of the system in less than 500,000 years. Well, it requires a disk dynamic that is staggeringly violent.
Like pinball physics.
Exactly. It requires extreme orbital eccentricities, perhaps gravitational scattering with other massive unseen companions in the system that flung it inward like a billiard ball.
And what if it's not a timeline or location issue? What if we are looking at a compositional defiance?
What do you mean?
Say the host star is heavily metal poor. We know there are stars out there that are almost entirely hydrogen and helium, lacking the heavier elements like iron, silicon, and carbon.
Sure.
If CHEOPS found a planet with a massive, dense, rocky core orbiting a star that had no rocks to give, where did the material come from?
Oh, a compositional mismatch would be equally paradigm-shattering. The fundamental assumption of planetary science is that a star and its planets form from the exact same primordial molecular cloud.
Right, they should match.
They should absolutely share a chemical fingerprint. If you find a heavily metallic planet around a metal-poor star, you are forced to consider radical scenarios. Did the planet form in a completely different star system, get ejected as a rogue planet, wander interstellar space, and then get gravitationally captured by this young star?
Capturing a rogue planet at the exact right velocity to circularize an orbit close to the star seems statistically absurd.
It is incredibly improbable. Capture usually results in highly elliptical, unstable orbits. To find a circularized, massive planet with a mismatched composition would suggest that rogue planets are vastly more common than we ever estimated.
Or that capturing them is easier than we thought.
Or that planetary capture mechanisms are much more efficient than our physics currently allow. Yeah. Alternatively, it might suggest that heavy elements can segregate and concentrate within a protoplanetary disk in ways fluid dynamics cannot currently explain, creating highly localized metal traps, even in an otherwise impoverished disk.
It is so wildly complex. Humans are intrinsically drawn to rules. We build our entire societies on predictable frameworks, and we expect the physical universe to behave the same way.
We want neat little boxes for everything.
We really do. It gives us a profound sense of safety to look up at the night sky and think, yes, standard core accretion is happening up there, a very orderly, predictable progression. But honestly, there is a deep primal thrill when nature looks at our mathematical models and just flatly refuses to follow them.
There is an undeniable thrill, but it's not just about the intellectual puzzle. If we step back and ask why this matters, we have to look directly in the mirror. Planetary formation models are not just abstract academic exercises. They are the foundational narrative for how we understand our own origins.
Right. Earth, our entire history is predicated on these rules.
Everything we understand about our home, how the Earth accreted its mass, how the catastrophic impact with a Mars-sized body formed the moon, how water was delivered to the surface by volatile-rich asteroids migrating inward from the outer solar system, how our atmosphere evolved. It is all built on the bedrock of the core accretion model.
So if the foundation is cracked,
if CHEOPS is demonstrating that planets can form in wildly defiant, unpredictable, and accelerated ways, it forces us to confront a massive blind spot in our own history.
we might be fundamentally misunderstanding the incredibly chaotic, improbable sequence of events that led to a habitable Earth.
Exactly. We assume our solar system is a standard blueprint. But if gas giants can form in 300,000 years and violently migrate inward, what does that do to the delicate, slow-forming, rocky planets in the inner system?
I mean, a migrating Jupiter sounds pretty destructive.
A migrating gas giant acts like a cosmic wrecking ball. Its immense gravity would scatter planetesimals, ejecting proto-Earths into interstellar space or plunging them into the sun. If rapid formation and violent migration are common, stable terrestrial planets like Earth might be far rarer than we hoped.
That's a scary thought.
But conversely, rapid formation might be the very mechanism that efficiently delivers the chemical precursors for life to the inner system.
That is a staggering thought. If the recipe for planets is wrong, then our understanding of our own kitchen is fundamentally flawed, which leads us to the vast ripple effect of this March 2026 discovery.
The ripples are huge.
You cannot simply break the laws of physics in one isolated corner of the universe and expect the rest of astrophysics to carry on with business as usual. If the fundamental recipe is wrong, then the places we expect to find planets, and perhaps life itself, must be entirely reevaluated.
This is exactly how a single, verified anomaly expands into a universal paradigm shift. When an observation like the CHEOPS data is confirmed, it acts as a catalyst for rapid, creative chaos within the scientific community.
Chaos is a good word for it.
The immediate aftermath is one of total destabilization. Old, established models are heavily annotated with question marks.
I can only imagine the scrambling happening in university physics departments right now. The frantic rewriting of grant proposals, the sudden pivot of doctoral theses. You have thousands of brilliant minds realizing the textbook they've been studying is obsolete.
Absolutely. And from that chaos, wild new hypotheses are born. Theoretical physicists are being given the explicit permission to think outside the box in a way they haven't been since the discovery of the first exoplanets in the 1990s.
They're allowed to get weird again.
Exactly. They are running entirely new supercomputer simulations, tweaking variables they previously assumed were constant. They are sketching out new mechanisms for magnetic braking, exploring the role of cosmic rays and ionizing protoplanetary disks to induce turbulence, and rethinking the hydrodynamics of gas collapse.
So let's bring this down to the human level. For you, listening right now, trying to make sense of our place in the cosmos. If the rules of planetary formation are completely broken, what does that mean for the ultimate question? Are planets more common than we thought, or way rarer? Are we more alone in the dark, or are we surrounded by worlds we didn't even know we should be looking for?
Well, if we connect this anomaly to the bigger picture of exobiology, the answer leans heavily toward a vastly more diverse, more crowded universe.
Really? A crowded universe?
Yeah, our entire search for extraterrestrial life, our strict definitions of the habitable zone or the Goldilocks zone, is heavily predicated on knowing exactly where and how planets form.
Right.
For decades, we have been scanning the skies looking for specific types of main sequence stars at specific ages, expecting to find specific types of rocky worlds orbiting at a distance where liquid water can pool on the surface.
We've been looking for Earth 2.0. We've been assuming the only way to bake a habitable planet is to use our exact solar system as the recipe.
Exactly. We assumed that if a star was too young, it couldn't possibly host a mature planetary system. We assumed that if a binary star system had too much overlapping gravitational turbulence, it would tear young planets apart before they could form.
We assumed a lot.
We assumed that regions heavily depleted of heavy metals were barren.
But if CHEOPS proves that planets can bypass the millions of years of slow accretion, if they can form violently and rapidly, or survive in totally chaotic environments,
it vastly expands the habitable real estate of the universe. It implies that worlds capable of harboring complex chemistry might exist in environments we previously dismissed as dead or impossible.
we had our scientific blinders on.
We really did. We assumed nature operated like a rigid factory assembly line, but CHEOPS is aggressively suggesting that nature is far more improvisational.
You know, it makes me think about rogue planets again. We touched on them briefly, but if planets can form via rapid disk instability, could they be ejected just as rapidly?
Oh, definitely.
We've historically thought of rogue planets as tragic, frozen worlds wandering the void. But if they form quickly and get ejected while they still retain massive internal heat from their formation, or if they take a large, icy moon with them.
That is a highly active area of speculation right now. A massive rogue planet ejected from its young system would retain a tremendous amount of primordial heat and radioactive decay in its core.
So it brings its own heat source.
Right. And if it had a moon, the tidal forces exerted by the giant planet could flex the moon's interior, generating enough frictional heat to sustain a subsurface ocean of liquid water, much like Jupiter's moon Europa.
Wow.
You could theoretically have a habitable environment, a thriving biosphere in a dark ocean, wandering the interstellar space entirely completely decoupled from a host star.
A completely starless ecosystem. That sounds like sci-fi, but it's grounded in this new data.
Entirely possible under these revised models.
Okay.
And consider binary star systems. Roughly half the stars in the Milky Way are in binary or multiple star systems.
2 suns like Tatooine.
Exactly. The old core accretion models struggled to explain how a stable protoplanetary disk could exist long enough in a binary system to form planets. The overlapping gravity of the two stars should disrupt the disk and scatter the pebbles.
So they shouldn't exist.
Right. But if a planet can form via rapid, localized instability in just a few thousand years, it can essentially coalesce before the binary stars have a chance to tear the disk apart. This implies that billions of binary star systems we previously ignored might actually be teeming with planets.
The possibilities for where life could emerge just multiplied exponentially because we realized our old rules were too restrictive. This perfectly transitions us to the future. We've looked at the break in the data, we've explored the complex physics of why it shouldn't exist, and we've discussed how it fundamentally alters our search for life. Now we have to look forward.
What comes next?
Yeah. How does science actually proceed the day after a foundational theory is shattered? What is the long-term legacy of this March 2026 CHEOPS discovery going to be? Because I really believe, looking back decades from now, this will be viewed as a historical turning point.
It undeniably will be. And this situation really highlights the absolute beauty and rigor of the scientific method. The general public often views science as a massive, static encyclopedia of absolute facts.
Which are already figured out.
A completed jigsaw puzzle where we are just polishing the final pieces. But it is not. Science is a continuously evolving, highly dynamic model. It is a process of getting progressively less wrong over time.
Less wrong. I love that phrasing. It strips away the hubris.
It is the reality of the profession. Every theory, no matter how elegant or mathematically sound, is just the best explanation we have until an observation proves it inadequate. The core accretion model was an incredible triumph of 20th century astrophysics. It explained the data we had at the time flawlessly. But when an instrument like CHEOPS achieves a new level of precision and makes a discovery that completely defies that understanding, it is not a failure of science.
It's the opposite.
It is a massive, celebrated triumph. It is the universe itself physically pointing us toward a deeper, more complex, more nuanced truth that our previous instruments were just too blind to see.
It's a paradigm shift. I think it was Thomas Kuhn who wrote about this, how science operates under a normal paradigm until anomalies build up, and then you have a sudden revolutionary crisis that forces a totally new worldview.
Exactly. We are entering a Kuhnian crisis right now, and it is the most fertile ground for new discoveries.
I think this is profoundly relatable to everyday human life, honestly. Think about your own experiences listening to this. Learning something that completely upends your personal worldview is initially overwhelming. It's deeply disorienting.
It's scary.
If you learn something about a close friend, or your career trajectory, or a core belief about yourself that breaks your preconceived rules, it triggers a crisis. You feel unmoored. But historically, looking back, it's also the only way true growth ever happens.
That's a really good point.
If you never have your worldview challenged, if you never encounter data that contradicts your beliefs, you are just walking in a tight, comfortable circle. Astronomy just stepped out of its circle.
That is a profound and accurate parallel. The friction of the unknown is where growth occurs. And this raises an important question for the immediate future. What will our next generation instruments find now that CHEOPS has forced us to broaden our imaginations?
It's the big guns.
Yeah, we have the James Webb Space Telescope currently operating, possessing unprecedented infrared sensitivity to peer deep into the atmospheres of exoplanets. We have the upcoming extremely large telescope, the ELT, being constructed right now in the Atacama Desert in Chile, featuring a main mirror nearly 40 meters across.
Up until this CHEOPS announcement, observation time on those billion-dollar instruments was incredibly precious and heavily influenced by our old models, right?
Yeah.
We pointed them where the math told us to point them.
We told them where to look based on what we thought was possible. If a proposal asked for JWST time to look for a massive planet around a 300,000-year-old star, the review committee would have likely rejected it.
If it would be a waste of time.
Exactly, citing the core accretion models that said it was a waste of expensive telescope time because nothing could be there yet.
But now, the leash is entirely off.
The leash is off. The observational parameters have been blown wide open. We are going to start pointing the James Webb Space Telescope and the ELT at regions of space we previously ignored as barren.
We're going to look everywhere.
We are going to intensely scrutinize the youngest, most chaotic T-Tauri stars. We are going to look at bizarre stellar remnants, white dwarfs, and neutron stars, searching for planetary signatures that survive the death of their host stars. We are going to search for atmospheric biosignatures in extreme environments that the old textbooks would have dismissed as absurd.
Because the absurd is now hard data. The absurd is on the table. Okay, let's pull all of this vast cosmic territory together. We have covered an immense amount of ground today.
We really have.
We started with a single startling moment in March 2026, a moment where the CHEOPS-based telescope stared at an infant star, captured the transit of a massive planet with unbelievable precision, and handed humanity an observation that utterly and completely defied a century of planetary formation models.
We examined an observation that survived every ruthless, skeptical test the scientific community could throw at it. It endured the detrending, the pipeline recalibrations, and the independent verifications, emerging not as a glitch, but as an undeniable, paradigm-shifting physical reality.
And from that single broken rule, we journeyed into the complex mechanics of how planets are born. We look at the slow, millions of years dance of core accretion, the hurdles of the meter-sized barrier, and the absolute necessity of the frost line. And we saw how this single new planet shatters all those requirements, forcing us to consider wild alternatives like rapid disk instability or violent chaotic migration.
We moved from the comfort of established linear physics into the thrilling, complex chaos of the unknown. We learned that by breaking the established models, we aren't just losing a theory, we are gaining a vastly larger, more diverse universe.
Exactly. We are radically expanding the potential real estate for life, realizing that habitable worlds might exist in the chaotic orbits of binary stars or the dark void of interstellar space. And we are forced to rethink the incredibly unlikely chaotic origins of our own home, Earth.
It really changes everything.
And the big takeaway here, for you listening to this, absorbing all this high-level astrophysics, is that being truly well-informed isn't just about memorizing the established rules. It's not about having all the answers locked down in a neat, tidy box.
A rigid mind is a fragile mind, especially in science.
Exactly. Being truly well-informed is about paying fierce, unrelenting attention when the rules get broken. It's about maintaining the intellectual flexibility to let the data surprise you, to let the universe prove you wrong, and to recognize that an incomplete map is just an invitation to explore further.
It is about embracing the anomalies, because the anomalies are where the truth hides.
So, we want to leave you with something to chew on, something to mull over tonight when you step outside and look up at the vastness of the night sky. If CHEOPS has proven that the fundamental, deeply established rules of how worlds are born can be totally and utterly defied, well, what other unbreakable laws of the universe are just waiting for the exact right telescope or the exact right mathematical model to prove them entirely wrong?
Yeah, what else are we wrong about?
Exactly. What if the rules of the cosmos we cling to so tightly are really just local customs of our specific solar system, and we're only just beginning to travel?
It makes you wonder how much of our perceived reality is just a trick of our incredibly limited perspective in space and time.
It really does. Because when you step out into the real unforgiving complexity of the cosmos, you realize that comforting need for a clean, simple binary answer is an illusion. The universe isn't a neat equation waiting to be solved. It is a wildly unpredictable, deeply creative living mystery. And honestly, we wouldn't want it any other way.